Hello, how's your day? My name's Isaac and I'm a tutor at CWI. Today I'm going to make my first video for the embedded tutoring of Calculus 1. And I figured there's probably not a better place to start than when looking at slopes, or what we call in calculus rates of change. So you may remember when we dealt with lines, just straight lines, we used a formula of y equals mx plus b. And the m in mx plus b is the slope. And that's what pretty much calculus is all about, or at least half of it. And so let's take a look at no longer a straight line. We want to find out what the slope is at any given point on a curved line. And so I have a curved line here drawn. It's a function f of x, which means that you give it an input and it gives you an output. The input is x, the output's y. We call that the independent variable is x, and then y is dependent on x. And so as you can see here, we're evaluating this point right here. We could call it point P, and it has some x and y coordinate. But the important part about this point is that we're going to go a certain distance away from it. And so I'm going to call that certain distance h. And so on the input axis, the x-axis, I'm going to move a quantity h over to the right. And I'm going to call the new point x plus h. So I moved over h from x, which means that I'm now at x plus h. And because we changed the independent variable, that's going to cause a change to the dependent variable. So at f of x plus h, the height of our function is going to be the function f when you plug in x plus h. So now this height is the function when you plug in x plus h. So in other words, you plug in x, the function spits out f of x. You plug in x plus h, you get f of x plus h for the output. And as you can see, I've turned it into a triangle. So we're going to go ahead and zoom into that triangle. And this is parallel with the x-axis. That's perpendicular with the x-axis. We're going to go ahead and say, we're going to call this delta x and delta y. And the uppercase delta stands for an average rate of change. Not an instantaneous rate, we're not quite there yet. So, we know that we start at point P. We start at point P over here, which is at x. And in the y direction, it's f of x. So in other words, we're x over, and we're f of x up. Then we go over here to this new point we created by going over amount h. And what we'll find is that the point here, let's call it Q. Q is going to have an x value of x plus h. And it's going to have a y value output that's equivalent to f when you plug in x plus h. Alright. So now that we're here, we just need to remember what was slope when we talked about linear lines. Well, slope, we got the saying rise over run. Okay, so would you consider y rising? I would, because it's going vertically, and x is running. So if we're looking for rise over run, we're looking for the slope m is going to be equal to rise over run, which is equivalent to delta y over delta x. And when we're trying to find the amount something has changed, we take the value over here, the x value here, and subtract it from the x value there, the y value over here, and subtract it from the y value over there. And so you could write that as the change in y as y2 minus y1 all over the change in x, which is x2 minus x1. And we'll take that a step further, and we're going to go ahead and plug in our y2s and our y1s. So y at point 2, which we called q, is y2 is f of x plus h. And then we're going to subtract y1, which is f of x. And what that gives us is the delta y. So now we've solved for delta y using our unique points. And then we're going to divide by the x value, or x plus h is x2, x plus h. And then we're going to subtract x1, which is just x. And what you'll find here is that the x's actually cancel on the bottom there. So m could be written as f of x plus h minus f of x all over h. And this is an approximation. And I want you to think to yourself, for this distance h, as h gets bigger, what happens to the approximation? As h gets smaller, what happens to the approximation? So if h got really big, like say h brought us all the way to over here, you would notice that the slope we created is not in fact very similar to the true tangent of the curve at that point. And so we can extrapolate that as h gets smaller, we're going to keep getting closer to what we call the instantaneous rate of change, or the true tangent line from this point. And so at this point, you can use this formula for approximations. But where we're really heading with this, because we've talked a little bit about limits, is we're wondering, what is the limit of this function as h approaches 0? And this is actually, like we said, as h gets really, really close to 0, our approximation is no longer an approximation. It's actually the true slope. And this is the definition of what we call a derivative, and we'll cover more of that later on. But for now, just realize that you can actually use this approximation formula to solve for the slope. And so I'll do a video next going through an example problem. Thank you.